All right, here's the bell work. I'm going to write an equation for this, and then we'll use the equation to find how many text messages Brad would send in 30 days. So this is what we get if you use the M and D, M for messages, D for number of days. You could have used y equals 50x if you'd like. And just so we understand, 50 is the rate of change or the slope on this one, because in the table it's showing that he's going to send 50 messages here in this one day. So that's a 50 to 1 ratio, which is the rate, 50 messages per one day. So to use the equation to figure out how many messages you would send in 30 days, y equals 50, but now instead of x, it's just 30 right here. So 50 times 30, that's where we get the 1,500 from. But don't forget to label that because it is a word problem. It should be labeled in messages. Here's our objective. I can graph any function, linear or nonlinear. All right, here are two words that we need to be familiar with for this section. Linear and nonlinear. So there's three ways that we look at linear and nonlinearity, and that's through tables, graphs, and equations. So for a table, in order for it to be linear, you'd have to have a constant rate of change. And on a graph, what you'd be looking for is a straight line. So the constant rate of change forces the graph to show a straight line, which is really what linear means, is that you got a straight line. And then for equations, what we need to see is the x. Well, it should be some form of slope-intercept form. Some form of this. Now you could see x equals something, and it'd be linear as well, and we've seen those before, but again, if you think about the graph or the table, you shouldn't just have a straight line on the graph or a constant rate of change in the table. So nonlinear functions, and they can still be functions if they're not linear, but a nonlinear means it's just not straight, which also means that you would not have a constant rate of change. And then this last part, in equations, what you'll see is like x in a denominator, like you can have a number here. Sometimes you'll see x with exponents. Sometimes you'll see like a number with an x exponent. That's also would create a non-straight relationship for these functions. Or even absolute values of x's. These would be nonlinear. And that's kind of what we'll see. If you ever see anything like these in an equation or function, then you can know right away that it's not linear. Yeah, another one that you'll see is this absolute value of x stuff. If you see an absolute value of x, the x has to be within that square root, I should say, this square root symbol. If you see it within that square root symbol, then it's not linear as well. So sketch the general appearance of the graph. I'm not going to sketch this one. Well, I'm not going to go into too much detail for it, but if you saw a graph like this one with x and y axis, y equals mx plus b would look maybe something like this, right? Where you'd say, oh, I know my y-intercept right here, whatever that y value is, that's the b, and then the slope is just how far up and to the right this one would be. So we'd see the slope in the stair steps like we've seen before. And that's also rise over run. All right, so m is slope or rate of change, which is also rise over run. And then the b is, it's always going to be the x value 0. So yeah, in tables, we would look for anywhere in the table where it shows the x value 0. That would be our y-intercept. So what makes a graph linear? It just needs to be a straight line. That's all. All right, so here's some tables, and they've given us the equations for these. So just from the equation, we should know pretty quick if it's linear or not. Like in this first one, y equals x. We see that this one takes on the slope-intercept form, right? So it's really y equals 1x plus 0 right here, which is in slope-intercept form. So this one would be a straight line on a graph, so it would also be linear. Not that we need all that stuff, but we should know that. So I'm going to use the equation to find all of the corresponding y values, because all we have in the table are x values. So I'd say, okay, y equals x, but in this first one, we're saying that the x is -2 here. So I replace x with -2. There's not anything else to operate on with this -2, so the y is just -2 as well. And it's going to work the same if I put -1 in there. So there's -1. If I say y is -1, right, because I replaced the x with -1, then y is just -1. Or on that third one, if I replace x with 0, this one, then it shows that y is just 0. Now we should see matching because it says up here y is x. That means they just match. And so whatever we get in the x column, the y value is going to match. So we end up with something like this. So we know that the equation is linear because it can be written in slope-intercept form. We can know that the table is linear because as a ratio of change, the rate of change, right here is the y goes up 1, the x goes to the right 1. The y goes up 1, the x goes to the right 1. And we see that this pattern continues throughout this table, which is why this one would be considered linear. And so the graph for this one, I'm not going to do too much detail on this, but I know at -2, -2, we would get this point. -1, -1 is this point. 0, 0, 1, 1, and then 2, 2. So yeah, that creates this straight line for us. And the straight line on the graph is it's a quick visual proof that we have a linear relationship because it's a straight line. So y equals the absolute value of x. So y equals the absolute value of x. So in this one, it's just y equals the absolute value of what would be -2. And that's the absolute value. If we've forgotten about absolute values, that's okay. An absolute value is just asking how far away a value is from 0. So how far away is -2 from 0? It's 2. Or this next one, how far away is -1 from 0? 1. And then how far away is 0 from 0? 0. Well, then how far away is 1 from 0? It's still 1. And same with absolute value of 2 here. How far away is 2 from 0? It's 2 away from 0. Okay? Now we should think about what this graph would look like as well. So I'll just kind of graph it by hand real quick. So we got -2 and 2, something like this. And so -2, 2, that's this first ordered pair here. Then I got -1, 1, which would be this ordered pair. And then 0, 0 is right at the origin. 1, 1, and then 2, 2 would be these ordered pairs. Now we can see from this graph that while it is straight to the left of the y-axis, it suddenly cuts back like this, all right? So even though the two parts of this line are straight, like it goes straight this way, but then it cuts back this way, that means it is not straight all the way through. And just like we said in the objective, if you ever see absolute values of x like this in an equation, we should know pretty quick that this is not linear. And it can be proven in the table as well. I would say, well, the y goes down 1 while the x goes up 1. All right, now it has to be a constant rate of change. And while it is between these first 3 points, as soon as I go from 0 to 1, then it goes up 1 instead of down 1, and then to the right 1. So that changed. The rate of change changed from -1 to 1 ratio to suddenly being a 1 to 1 ratio. And those are not the same, although they may look the same. So this problem, y equals x to the power of 2. Again, we should see that x now has an exponent, 2 in this case. It wouldn't matter what the exponent is, as long as it's not 1, then it's automatically not linear. So this one we would know pretty quick right here, just from the equation that it's not linear. But let's show it in the table as well. So it's always x to the power of 2, right? So we're saying x is -2. We're going to make that to the power of 2. So you can put that in the calculator if you need to. Like on this one, and yeah, you would, for negatives especially, you're going to want to use those parentheses buttons. And then you got to push the negative button, not the minus button, to close your parentheses. And then you just need to find the x to the power of 2 button. And then when you push equals, it will give you the answer on this one. It's just 4. Or in your mind, you can do -2 times -2, which may be faster. I don't know. So this next one, we got -1 to the power of 2. So -1 times -1. Negative times negative is positive. 1 times 1 is 1. Positive 1. So let's try 0 to the power of 2. 0 times 0 is 0. Or this next one, 1 times 1, which is 1. Or 2 to the power of 2, that's 2 times 2, which is 4. All right, so we know from the equation that it is not linear, but we can know in the table that it's not linear as well, because here I have y, it drops by 3, where x goes up by 1. So that's a -3 to 1 ratio. And then suddenly it changes to down 1, and then to the right 1. So as a ratio, that would be -1 over 1, rise over run. And these two are not equal. So that's the rate of change between the 2 points. And they are not the same. As soon as they're not the same, for the rate, automatically, it is not linear. I forgot to make the graph on this last one, though. Not that it'll take very long, but I got 1, 2, 1, 2, 3, 4 x's and y. So we had something like this: -2, 4, -1, 1, 0, 0, 1, 1, and then 2, 4, something like this. Now, while this may seem like it would look kind of like our absolute value graph up here, it's actually curved. On this one, it kind of a U shape right there. And again, maybe your curves are better than mine, but it doesn't really matter. Okay? But that's what the graph would look like. And just from the first 3, we can see some curvature right there, which means it would not be linear. All right, y equals 1 over x. Now on this one, we see an x in the denominator, so we would know pretty quick, just from the equation, that this is not linear. And so just from the equation, we would know that, but let's show it with the table as well. So on this one, we're saying that y equals 1 over x. So the y value that I'm solving for is just 1 over the x value, which in this case is -2. I'm going to show the decimal on this one just because it may help us with the graphing. That's a -0.5. And then the next one would be 1 over -1. Put that in the calculator and you'll get -1. Next up, we have 1 over 0. Now your calculator is going to show an error on this one, okay, which indicates that it's going to infinity like this. And you may ask, well, which direction are we looking at infinity? We don't need to worry about that right now. You'll discuss this in a lot more detail in 9th grade. So for now, all we need is the ordered pairs, which should help us to look at the graph and to determine if it's a function or not. So next up, I'd say, well, then we got 1 over 1 over 1, which is just +1. And then finally 1 over 2, that's the last value they gave us, which is +0.5. So in the graph, the only thing we can know right now, because we haven't gone over this type of problem, is that we got -2 and 2 and something like this, right? We got ordered pairs at -2, -1/2, and then -1, -1, like this. And then also an ordered pair of 1, 1, and then 2, 1/2. The error one, we're not going to consider 0 and infinity yet. Again, you'll cover that more in 9th grade. So this is all we know about this. And no matter how we connect these points right here, we can see that this one is not linear. Okay, so that's from the graph, but how would we know that from the table? Well, it's the same thing right here. It goes up by 1/2. Well, down by 1/2. and then it goes, well, to the right one. So that's a 1/2 to 1 ratio. But then suddenly right here, where it shows an error, well, then we're looking at an infinity to 1 ratio, and these definitely are not equal. So the rate of change is changing throughout. So yeah, not a function, not linear on this one. In my opinion, it takes longer to do the tables just because it's not a visual representation, right? Like I could look at a graph and say, well, that's jacked up that it kind of like goes down and then back up kind of thing. And that's not really how this one acts. But if just based on what knowledge we have, I would look at this thing and know that it's not linear. And then from the equation, I would know it's not linear because the x is in the denominator. But from the table, there's actually some calculation involved. And sometimes it may look like it's not linear, but it actually is. We'll see examples like that. All right, this one is y is the absolute value of x. Well, so yeah, just from the equation, because of the square root, we can say that this one's not linear. We're just looking for anything that's kind of out of the ordinary for us right now. And since all we've dealt with is linear equations, square roots, absolute values, and exponents, yeah, they shouldn't. We should kind of feel a little weird about those right now because we don't have a lot of experience with them, which in turn should help us to understand that they are not linear. So right away, we know the equation's not linear, but let's find these values. Now, to access the square root, you're going to have to push the green button. It's in the top left on our calculators. It's the second button. And then you're going to push the x to the power of 2 button. And then on the screen, it will show the square root. And so this first one, I would type in 0 and then enter. Okay, so this would show as a square root of 0, which in your calculator should give you an answer of 0. So this next one would be the square root of 1. And when you put this in the calculator, you get 1 back. This next one may be a little problematic because when we type this one, the square root of 2, the calculator, I believe, just gives us the square root of 2 back. So you're just going to push the double arrow button right above the enter button in the bottom right, and it will change it into a decimal for you, which is, I'm going to round to the nearest tenth, 1.3. So that's 2, 1.3. That would be that ordered pair. And then next up, square root of 3. But again, the calculator should give you back the square root of 3. Just push that double arrow button, and it'll give you the answer there, 1.4. No, I was looking at the wrong one. It's 1.7. Yeah, this one's 1.4. Again, these are approximations. So 1.7 right there. And then when you put in the square root of 4, this one will come out nice. This is just 2. So 4/2. All right, and again, from the table, we can see the y, it goes up 1, and then to the right 1, which as a ratio is a 1-to-1 ratio. And then suddenly it goes up by 0.3. So that'd be our numerator rather. But it still goes to the right one. And these two ratios are not equal, so this would be considered not linear. And then finally, the graph for this one would look something like this. So we have 0, 0, 1, 1, 2, 1.3, about right there, and then 3, 1.7, and then 2, 4, right? And while my graph may be kind of poor, this one would, if you were to actually graph it, curves like this. And since it's a curved line on the graph, automatically this one would not be linear. So we see, and again, try not to get linear mixed up with functional. This is a function because it still shows that none of the x values repeat. And this line would pass the vertical line test. It's just that it's not linear. So it's a function, it's just not linear. It's not a straight line. Apologize, that's a typo, if you will. Yeah, that should have been a 4 right there. Thank you. All right, on this one, it's y equals 2 to the power of x. So for each of these, I'm going to take 2 and raise it to the power of x, which in this case is 0. So putting this one in the calculator, we don't need the second button, but you're going to look for this button right here. It's just right above the x to the power of 2 button, which is from the button 7, it's left 1 and then up 1. It's called a caret. So actually, first up, what you do is you type in 2. So you're going to type in the 2, and then you're going to have the power, and you'll see if you push that button that it changes the format in the screen. So now you're in exponent mode, and then you're going to type in 0. Then enter, and then look at what it gives you. That's your y value, which for these calculators should show 1. For any calculator should show 1 for this. Okay, and we're going to use this in order to solve for these other values. So that's next up 2 to the power of 1, which is 2. Next up would be 2 to the power of 3. Sorry, 2 to the power of 2. Now, it may be faster to type these in or to just do these in your head rather than type them in. I would still type them in just to check until you start doing better with these. But 2 to the power of 2 is 2 times 2. And some of you know faster than the calculator that this is 4. So next up, this would be 2 to the power of 3. Type it in, or you can do it in your head. 2 times 2 is 4, times 2 is 8. And some of you are even noticing the pattern here. We're just multiplying by 2 from each of these values. So you could say, well, 8 times 2 is 16. Or you could type it into the calculator. 2 to the power of 4, it's still 16. All right. Now, going back to the equation, we know this is not linear because it's got an x in the exponent, which is different for us. So this is not linear. But in the table, it would show the same thing. From 1 to 2, it shows up 1. And from 0 to 1, that's the run. That's to the right 1, which is a 1-to-1 ratio. But then suddenly it goes up 2, and then to the right 1, which is a 2-to-1 ratio. And these two are not equal. So the rates are not equal, the rates of change. So these are not, this is automatically here not linear. But on the graph as well, it would show the same thing. I can't fit very much on there, but 0, 1, 1, 2, 2, 4. And yeah, just from this, even if you were to connect these with straight lines, not that you should, but you can see that while the lines separately are straight, it changes direction right there. But really, this would be curved, something like this. And in fact, to the left, it just kind of goes along that x-axis. So right here, we can see this one's not linear. And again, you may ask, well, is it a function? Well, yeah, the table shows we don't have any x values that repeat, and also our graph, if I'd drawn it better, would pass the vertical line test. All right, here's two that we have seen, two types we've seen. And these types we should know, again, very quickly if they are linear or not. I don't see any exponents, no funky symbols like square roots or absolute values. The x is not in the denominator, so the equation would show that this is already linear. But let's show with the table as well. So the y value is going to be the x plus y equals 6, so we may have to use some solving equation stuff for this one. So the x first here is -2, and then plus y equals 6. Well, to solve this one, you just add 2 to both sides, just like you would a regular equation, and you get y equals 8. So the y value is 8. Or on the next one, the x value is now -1. So you'd have to add 1 to both sides. And so that zeroes out. Y equals 6 plus 1, which is 7. So the same thing on the next one, but now the value of x is 0. And yeah, well, I'm just going to make this one a phantom 0. So that shows y equals 6. And on the next one, we got 1 plus y equals 6. So I would subtract 1 from both sides to zero that out. And y equals 6 plus 1. I'm going to put minus 1 on this, should be minus. 6 minus 1, which is 5. And then finally 2 plus y equals 6. So subtract 2 from both sides to zero that out. And then y equals 6 plus, dang it, I did it again, minus 2. 6 minus 2 is 4. And so we can see the pattern in the table. I mean, this one took a little bit more work with the equation, but from 8 to 7, that goes down 1, and x goes to the right 1. So that's a negative 1 to 1 ratio. And from 7 to 6, this goes down 1 again, and the x goes to the right 1, which is another negative 1 to 1 ratio. So those are equal. And even if we skip this next box, which would show a negative 1 to 1 ratio, and you will see this up from time to time where it skips like this. From 6 to 4, this would go down 2 instead. But the x values, the run, would show to the right 2 as well. So that's negative 2 over 2. And yeah, these actually are still equal, even if they're shown or scaled a different way with these fractions. So be careful on those. Again, this would be a case where you would say, well, it looks like it's different, but in fact, as a ratio, it is still the same. So, the graph on this one, we got 1, 2, 1, 2. Yeah, we get these ordered pairs. Negative 2, 8. Negative 1, 7. 0, 6. 1, 5. And 2, 4. So if I draw this a little bit better, it'd be an even better line. But this is the line we get. And yeah, this graph shows that it's straight. So this equation is linear. Which again, we expected from the beginning because the x isn't in a denominator, there's no exponents, no square roots, no absolute values. And then y equals 6. As an equation, this is actually y equals 0x plus 6, like this one, which shows the slope and y-intercept. And yeah, since it can be written in slope-intercept form, it's automatically a function. Well, also linear as well. But we should know what the graph of this would look like. In fact, the only values we can put in the table are values that make it true. And the only y value that's going to make this true is 6. So we'll just run through and put 6's in here. Like this. And yeah, from the table we can see that not only is it a function, but also that it's linear because this one is showing a change of up 0 and then to the right 1. So that's a 0 to 1 ratio, and this would be the same. It's plus 0. Doesn't even matter how far down you go. You could say, well, I'm going to go down 2 boxes. Still shows up 0, but now to the right 2. And a 0 to 2 ratio is the same value as 0 to 1 ratio. So that shows from the table that it is linear. And we should remember what the graphs of these ones should look like, because we've done several. So I've got negative 2, 2, 3, 4, 5, 6. So I'd have negative 2, 6 here, negative 1, 6, 0, 6, 1, 6, and 2, 6. And so yeah, we get a straight line. I know I didn't draw it straight, but that would be a straight line. It's just horizontal or flat. Yeah, so y equals 6 is linear. I forgot to put that on there. All right, so this last part of the worksheet is just showing, and we graphed them ourselves anyways, but it's showing the matching, like y equals x, it would look like this. Y equals absolute value like this. and then y equals 6 looks like this. And again, we know just from the graphs, since this one changes direction, it's not linear. This one is just a straight line throughout, so it is linear, and this one is straight throughout, so it's linear as well. Or y equals x to the power of 2, it's curved. This one's drawn much better than I did it, but it's curved, which automatically means this one is not linear. And this is the one that we haven't seen yet. You'll do this in more detail, either 9th or 10th grade. But we see some curvature on the insides of these. And since there is curvature, it's automatically not linear. X plus y equals 6, yeah, this one's just a straight line, so it is linear. And then these two, yes, y equals the square root of x, again, curvature, y equals 2 to the power of x, curvature, it's not straight, therefore these two also are not linear. All right, consider the area of a square as a function of the side length of a square. All right, we need to go back a little bit because this is saying it's using this wording. The area is a function of the side length. So remember, it's always y is a function of the x. And the table kind of gave this to us anyways, but the area is a side length, is a function of the side length. So that means side length is x, which is independent, and area is the y's, which are dependent. Dependent is a function of independent. Now they've drawn these pictures for us, which is very nice, but with squares, hopefully we don't need these because the unique thing about squares is the side lengths are all the same. And to find the area of a square, you just take the side length and multiply it by, well, itself, because the side lengths are the same. Just like you would with a rectangle, but now the side lengths are the same. So that shows an area of 1. So if the side length is 1 on a square, the area is 1. So I can start filling in this table. And on this next one, it shows side lengths of 2, which means if I wanted the area, it would be 2 times 2, which is 4. And yeah, it showed it right there for us, but this is how we're going to do this. So the next one doesn't have to be drawn to scale, but this is a 3 by 3 square. So the area would be 3 times 3, which is 9er. So that's a 3, 9 area. Side length 3, area 9. And then, of course, the next one would be a 4 by 4. So the area would be 4 times 4, which is 16. And then finally, a 5 by 5 square. So the area on this one would be 5 times 5, which is 25. So that helps us to fill in the table. And just looking at this table, we should know, first of all, that it is a function, just like we've gone over, but is it linear? Well, we could look at this and see that it's not linear because here we have up 3 to the right 1, but then suddenly it's up 5 to the right 1, which is ratios. That's a 3 to 1 ratio and a 5 to 1 ratio. These two are not the same, so it's not linear. Now the graph should show that it's not linear as well. So let's go ahead and label the axes because they didn't. They scaled them for us, so that's fine. So we got the side length, that's the x's, and then the area, that's our y's. And yeah, we just have these ordered pairs. So we got 1, 1. And be careful on the scale on this one. A lot of students make the error of putting the first ordered pair here, but the y scale is going up by 2's each time. So that's 1, 1 right there. And then we'd have 2, 4, which would be this point here. And then 3, 9. Again, I got to go in between the lines. And then 4, 16. Yeah, we won't be able to fit 5, 25. Now, you could think, well, what if the side length 0? What's the area? 0 times 0 is 0, which would just give us the y-intercept right there. And we can see curvature already for this one. It's well, something like this. So obviously this is not a straight line. And yeah, we can say which one's dependent and independent. Remember your x's on the left and y's on the right. X's are always independent and y's are dependent. I know it said that up here as well. All right, write an equation to model A as a function of S, no problem. And just be careful on this one. If you use A I wouldn't do s times s, I'd do s to the power of 2. I mean, you can, but some people would be like, that doesn't look right. Now, if you don't want to use a and s, you don't really have to, because we know the area is the y and the side lengths are x's, so it'd be y equals x to the power of 2. And that would be fine as well. So does this graph pass through the point 8, 64? Now, if it does, then that's saying that this is the side length is 8. So up here, we'll just kind of test it out. We'll say we've got a square here, side lengths of 8, which means the area is 8 times 8. Now, if this equals 64, that would be the area, and it does. So since it does equal 64, it is that ordered pair. So the answer is yes on this one. This graph will eventually go through the point 8, 64. So yeah, what does the point represent? It says, since it's 864, remember the x's are the side length, the y's are the area of a square. So it's like saying you got a square with the side length of 8 with an area of 64. All right, so list some other ordered pairs, and yeah, this is just some that are shown down here. Like if you had a side length of 6, 6 times 6 is 36, that's the area. If you had a side length at 7, 7 times 7 is 49. Or if you had a side length of 10, 10 times 10 is 100. So these would work. There's, of course, others that would work, like 864, 90, 81, 11, 121, and so forth. But these are the three that we chose. All right, is it linear? Yeah, we've already answered that. It's not linear, not only because the graph is not a straight line, but also because in the table we showed that it does not have a constant rate of change. All right, what about perimeter of a square as a function of the side length of the square? Well, the side length is 1. Yeah, if we just look at any square, it doesn't really matter. Remember, to find the perimeter, you're actually now adding the side lengths together. So if you had side lengths of 1 like this, then it'd be 1 plus 1 plus 1 plus 1, which gives you a perimeter of 4. And so let's change these. Let's say that the perimeter then was, or the lengths were 2. That's 2 plus 2 plus 2 plus 2, which is 8. So next up, change the side lengths to 3. So that's 3 plus 3 plus 3 plus 3, which is 12. And what about if the lengths were 4? Well, that's 4 plus 4 plus 4 plus 4, which is 16. And then finally, if the lengths were 5, 5 plus 5 plus 5 plus 5, which is 20. So we have all these values. So yeah, if you wanted to, you could have just multiplied those by 4. Yeah, you'd get the same answers on those. So, so that's our table. And from this table, we should know that this is linear because it does have a constant rate of change. We'll get more on that too in a second. But our first point here is 1, 4 at this point. And then I got 2, 8 here. And then 3, 12. 4, 16. And then 5, 20. Yep, and this one is showing with these ordered pairs that this would create a straight line right here, okay? So it's a straight line, therefore it is linear. So which of the variables is dependent and independent? Well, again, the table's always set up with x's and y's like this. And the y's are always dependent and the x's are always independent. So yeah, perimeter, which is the y values there, depending on the side length, which is the independent variable. So write an equation to model p as a function of s. So if we did this strictly as the way that we did it, and yeah, I'll keep using p and s on this one. So the perimeter would be the side length plus the side length plus the side length plus the side length. But if you wanted to simplify that using multiplication, you could just take 4 times s. Either one of these would work on this, okay? And yeah, if you look at the equation like this one takes on the form of slope-intercept. The slope is 4, the y-intercept is 0. So that means you'd have a y-intercept here at the origin, 0, 0. So what are some other values we could use? Yeah, if you had a side length of 6 right here, then you do 6 times 4 is 24, or 10 times 4 is 40, 100 times 400 is 400. You didn't have to use these exact values, but if you did, that's fine as well. Like if you said, well, side length is 7, 7 times 4 is 28, you could have gotten that one as well. So what does the point 1040 represent? It means that, again, this is x and y, and the x is side length, the y is perimeter. It means if you had a square with the side length of 10, its perimeter would be 40. So that's a square with the side length of 10 has a perimeter of 40. That's correct. There we go. And yeah, we know from the graph that it's linear because it's a straight line. And then in the table, it shows a constant rate of change, right? So you go up 4 to the right 1, which is a 4-to-1 ratio, or up 4 to the right 1, still the same ratio, up 4 to the right 1, still the same ratio, and up 4 to the right 1. Now remember, even if you had like an 8-to-2 ratio on this, it would still be equal. So it still shows that it's linear. So describe the basic structure of an equation. That's kind of what we talked about in the objective in the beginning. If the x variable cannot be in a denominator or show exponents or square roots or absolute value stuff. As long as you don't see any of that stuff in an equation, then you know it's linear. If you start seeing x in the denominator or with exponents or absolute values or roots, then it is automatically not linear. So there's our objective. You should not only be able to graph any function, but you should know if it's linear or not linear.